Okay, so there are two types of representations we're going to do it today, and they basically follow the same pattern. So I could have showed you how to do energy level diagrams first or electron configuration. It really doesn't matter, okay? So we are going to show the distribution of electrons. So in these two ways, no longer do you need to show how many protons are in the nucleus or how many neutrons, because again, for chemistry, electrons are where it's at, okay? So we're going to stick to just electrons. And it is a way to incorporate that we're thinking 3D now, like so spheres, dumbbells, clovers, instead of the flat 2D orbits that Bohr used, okay? So just so you have the terms, I guess, sometimes this can be annoying. So the shell is the main energy level. So still, essentially, we're talking about sometimes the period, and then again, it gets a little bit complicated when we get to the transition metals, and that's why in grade 9 and grade 10, maybe even last year, I would have said, oh, skip the transition metals, okay? Because we just didn't have enough to deal with them, and now we are going to deal with them. And then the subshell is going to, we're going to use the letters S, P, D, F. So again, spherical, polar, diffuse, fundamental, but we're lazy. We're just going to write S, P, D, F, okay? Oh, is somebody writing this out? Am I okay? Stop me if it's too fast. Okay, so we are going to still write the principal energy level value. So 1, 2, 3, 4, those kinds of things. And then we are going to use the letters as well, okay? So the next slide shows you an example of what this should look like. Oh, not the next slide. Some slides later. Oh, wait. Just a second. Hang on. This isn't the right one. Hold on, sorry. Okay, so we have already done this before, but we're just going to, here it is again, okay? When you have a value of 0, then that's the S, and there's only one sphere. When you have the possibility of 1, then that's going to be P with 3 orbitals. When you have 2, then it's going to be D with 5. When you have 3, it's going to be F with 7. But the periodic table is set up so you can see that pattern and you can count the columns, and you really don't even need to necessarily memorize it. So I sort of like watermarked this triangle picture, and it didn't even really print on your sheet very well, but that's perfect because who cares, okay? We are not going to draw these shapes like this. We are going to write electron configurations, okay? So if you have 2 electrons in each orbital, then you're going to multiply by how many how many different types there are to get the total, okay? So 1s orbital, 1 times 2 is 2. 3 p's, 3 times 2 is 6. 5 times 2 is 10. 7 times 2 is 14. We did that with this yesterday. We went 2, 4, 6, 8, 10, 12, 14, right? So instead of drawing the shapes, we're going to use numbers and letters S, P, D, F. So that also corresponds with the periodic table, okay? So we'll look at that in a second. This is very important. Actually, let's make a highlight around this whole box. Now, once you see how to use the periodic table, this should be like second nature, okay? So you'll know this like the back of your hand because you'll be able to count the columns on the periodic table to help you do this. So right now, do you need to know this? Does it have to be memorized? Sort of, but eventually you'll be like, oh, I can figure this out, which is good. So even though we are going to, yes. So if we go by this, so there are 7 possible shapes. 1, 2, 3, 4, 5, 6, 7 Fs, okay? And 2 electrons go in each. 2, 4, 6, 8, 10, 12, 14. So that is the maximum. So then in the bottom here, when you write an electron configuration or an energy level diagram, your last electrons it's called the F block. How do I know it's F? 1, 2, 3, 4, I'm counting columns, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? Max. S, max 2. We've always started with 0, right? 1, 2. P is next. The 0 and then -1, 0, +1. P is 6. 1, 2, 3, 4, 5, 6. Then D, there's 5. 5 times 2 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the column, not the rows. You just did it backwards. Yes. Now, well, once we do one, you're going to actually see how it does correlate with the columns and the n value, but you're right, yes. Okay, so, let's always keep Heisenberg in the back of our heads. So Heisenberg said it's called his uncertainty principle. So you cannot know the exact position and speed of a particle that's as fast as an electron. So you don't, and the reason we have to say this or think of this is we are not going to do things like how many electrons in px or py or pz. We don't need to do that. It's just p total, okay? This goes against Heisenberg's uncertainty principle. You don't need to say Is it in P, X? Is it in the Y? Is it in, that's too far. We can't know that, okay? We can say, is it in the P orbital? Somewhere in the region of 3D space, yes, but we do not need to be this specific, okay? So there's that, which is helpful. Okay? So here's this now in your note, right? So we're still going to use the big number. So actually, let's do this first. So eventually, what we're going to do is make something that looks like this. So we still have the principal quantum number. We're going to say where the shape is. And then we're going to say how many electrons are in the orbital. And this, all you're going to do is count, okay? So the pattern is going to be very similar. And I see students on the test, like literally moving their finger around the periodic table. That is a great way to do it because we're going to still follow conventions that you would have before. You would start with hydrogen, yes, and then follow 1, 2, 3, 4, 5, right? You naturally go up by numbers. That's what we're going to do. The modified periodic table that I gave you looks a little bit different because it's clumped together, the hydrogen and the helium, to make it a little bit easier for when you're considering how many electrons it has, okay? So you can use this periodic table, you can use that one, and the only thing that's on that periodic table is the atomic number because that's all you need, right? How many electrons does it have? You look at that number. Now, it can be frustrating for something like, say, tin, which its symbol is SN. Then, you know, if you're looking for T, maybe for tin, so it doesn't have names on there. So that can be a little bit frustrating, but you kind of get used to it. So no longer do we need to skip things like tin. We are not just going to stop at the first 20. Now we can do them all. So Bohr, one of his fundamental problems was that he said that the farther electrons were from the nucleus, that meant they had higher energy, and that's not always the case, okay? So we are now going to do lowest energy orbitals first, which is not necessarily the lowest n value. So it is not going to go in order of n. You are not meant to make it go in order, okay? You have to follow energy. How do we follow energy? You follow the periodic table. So that's why, like I said, I literally see students going like this, okay? You know, it's not your job to make them go in order, right? You have to follow the periodic table, the energy level. That's what you have to follow. Yes. Oh, how do we follow? Yes. Let's do it. So get out. Now, to me, this is too small. I don't like this. You can certainly write on here, but I gave you a big one, okay? So is there anybody who didn't get one? It made it all the way to the back? Amazing. Okay, so I am a colorful person. If you have colorful pens, this is your moment here. So we are going to add colors to this. So again, it is not mandatory for you to use this modified periodic table. It is really only useful for electron configurations and energy level diagrams because it gets rid of the extras, okay? So it's pared down to what we need. It's got the symbol and the number, that's it, okay? Okay, so in the back of our heads, we are thinking about the chart you filled in here, the maximum number of electrons as well. So what's the maximum number of electrons that go in S? 2. So this column, it says S1 up here. So every single one of these elements, their last term in their electron configuration is going to be S1. This column will be S2. Okay, so we call this the S block. What comes after S? P. Okay, so there's nothing over here. Okay, so then there would be some more S's, and then we get to P. This says 2P over here. I don't know, my eyes don't like that. So I'm going to rewrite that. I pick a new color. I got red. This is 2P. So first column is P. And what's the maximum for P? 6. Beautiful. The convention is to write it in the top right-hand corner. Sometimes people write it in the bottom. I won't take marks off for that, but try not to do that, okay? Six P's, 6 columns. P block. I'm too short for this. So if you want, actually, let's go through and label them all. So this is 2P, this is 3P, 4P, 5P, 6P, 7P. I didn't do that over here. If you want to do that, S, S, S. So this is the row, second row, third row. This is like in the P block. This is 1. How many electrons? 2, 3, 4, 5, 6. Maximum is 6, so it matches. So let's say you were going to do boron. So boron's last term would be 2p1. Carbon, 2p2. Nitrogen, 2p3. That's what we're going to do. Yeah, that's what we're going to do. Yes. Well, because it was already printed, so I had to like sneak it in. Well, Bohr said it was the distance from the nucleus, which also implied that the farther you got was highest in energy. And here is where he started to fall apart. So we've got the first 20 and then the transition metals. So how do we deal with that? That's what you guys asked me, right? How do we deal with the fact that sometimes the closer or the farther from the nucleus is not the highest in energy? So, for example, so we do argon, which is 18, 3p6, right? And then what did we tell you? We do 288, and then we were like, oh yeah, make another shell. So potassium, 4s1. Calcium, 4s2. However, if you have 2n squared like we did yesterday, and n is 3, what was the maximum electrons that should go in the third? 18. That is not what we told your grade 9 and 10 selves, is it? No. So, how do we rectify that? So when you get to this middle section, which we're going to call the D block, why D? Let's do the columns first. So this is D1. What's the maximum for D? 10. Good. Whoops. So how do we fix this? Okay? So what they found was that even though, once you get to scandium, even though these electrons in scandium were technically in the third energy level, they were actually higher in energy. So the scandium element, once there was enough electrons, fills the 4s first, and then the D. So when you get to the D block, it's actually n minus 1. So this is 4s, the fourth row. This is going to be 3d. This is 5s. What will this be? 4d. What's this? 6s, 5d, 7s, 6d. Okay? So I'll write that down. I don't need you, Siri. So I wrote row instead of period because I know that can kind of be confusing. You can write period if you want. You could write n value, principal quantum number, whatever, okay? So just, I am excited for this. I want to show you guys. So let's do zinc, okay? So when you, actually I'll read it here. We're not done yet, but F is so rare. Let's do this one. If I can find my pen. Here we go. Let's do zinc. Actually, I'm going to leave it green. Oh. Okay, so remember that one of the big advantages of this is that we do not have to skip anymore. So we can handle zinc, which has 30 electrons. I know we're not quite done, but let's just take care of zinc, okay? So when you do this, you always have to fill the lowest energy first. And what you can do is just go back to number 1. Start at 1, right? Logical, okay? So you go up here. Now, there is a bunch of ways to think about this. You're going to find that these look very, very similar. One of the questions in the homework, I think, is literally write the electron configurations for the first 4 halogens or something. And you'll notice that so much of it is exactly the same, okay? Because we're always going to start at the beginning. So we need to account for 30 electrons. Do I care how many neutrons and protons in this form? No, I do not, okay? So that's why this modified periodic table does not have that information, okay? So 1s2, is that filled? Yes. There's nothing over here. Then we go down here, 2s2. Okay, then we go over here, 2p6. Three s2. 3p6. 4s2. Okay, so all I have done is go along, la la la, go along. This is fine. Follow Bohr's rules. We're still good. 1s, then 2s, then 3s, then 4s. And 4s2 ends at calcium. So for the last 3 years, that's where we ended, right? You guys did the first 20 and that was it. Okay? Zinc, of course, is element 30. It is not part of the first 20. So how do we deal with that? So this tells us the number of electrons. Now, if you're not a mental math kind of person, just add in your calculator, okay? What's 2 plus 2? 4. Plus 6, 10. Plus 2, 12. Plus 6, 8. Plus 2, 20. Now, we need to account for 10 more to get to 30. How do we do that? Oh, yes. Look here. Zinc is in D10. Wonderful. But remember, this is where Bohr fell apart. He would have said 4D10. He wanted the farther away electrons to be higher in energy, but they just aren't. So how do we deal with that? We do, for the row, for the D block, n minus 1. So even though this is the 4th row, n minus 1 means 3D. So we write 3D10. So up to here was 20. What's 20 plus 10? 30. Okay? It is not, you're not going to write 3p6, 3d10, 4s2. No, that's not how it works. Okay? So how do we rectify the problem with Bohr's diagram? Just follow along. Okay? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, n minus 1, 3d10. And then if we had to go past, then we would go 4p6, 5s2, 4d10 until you get to your element. Okay? Yes. Oh, just follow the atomic number, okay? So number 1, number 2. Is zinc, or does zinc have 2 electrons at least? Yes. So we write them down. Then we keep going. 2s2. Does zinc have at least 4? Yes. Keep going. 2p6. Does zinc have at least 6 or 10? Yes. Keep going. 3s2. Okay? So there are a bunch of ways you can kind of double check your answer. You should know that S has a maximum of 2. So check all your S's. Do they have 2? Yes. Then check all your P's. They should have 6. Okay, I'm good. D has 10, okay? Again, in the end, you can double check the overall count to make sure that you get 30 or whatever the number is. Yes. Yes. So another thing you can do is look where it is, and that will tell you what your last term will be. So you can be like, okay, copper 3D9. I'm going to check. I got 3D9 at the end. Okay, I'm probably right. All right. So let's say Jaden said let's do copper. Okay. So if it was copper, I would write, start at the beginning, 1s2, nothing over there. 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Virtually identical except the last term. What would nickel look like? Same, 3d8, right? So it's the same pattern over and over and over again because what do we start with? Element 1. Why do we start with element 1? It's the lowest in energy, okay? So how does this help to rectify what Bohr would have said, okay? So let's say you had the second shell. I erased it, but if you had 2n squared and n was 2, how many electrons go in 2? 2 squared is 4 times 2 is 8. So let's take a look at this. All of the n values that have 2, how many electrons do they have? 8. Good. What about when we get n equals 3, we wanted 18 electrons, which is not what we told you in grade 9, 10, 11. Yes? How can we rectify this? Let's look at all the 3's. 2 plus 6 is 8, plus 10, what is that? Oh, 18. Okay? So Bohr was not completely wrong, and that's why we still give you that as a fundamental basis. But it was just too simplistic, okay? So there is, I'm just going to go back to this one for a second. There is this diagram is from your textbook. So this is another way. It's got it already filled in. If you like that, you can look at that, okay? So the big thing is to do the increasing energy, which is not the same as increasing the n value. Up to 20 is easy. It's once you get to those transition metals. And before, we would have said skip the transition metals. Now we're going to deal with them, okay? Okay, let's do the last one. Pick your last color. I'll pick pink. So we have S, we have P, we have D. What's next? What letter's next? Good. And how many are in F? 14. Now, lanthanides and actinides, we've been telling you for years, are weird, right? They're removed from the periodic table. So we're going to assume then that they also have a little bit of a quirk to them, okay? But if this is n minus 1 for D, then the next one, how do you figure it out? Do n minus 2. But here's the extra annoying thing. Do we call this 8, 9? No, because look what we've done. This is 56, barium. Where's 57? Okay, so technically, this goes here. So that means that it's 6, row 6, minus 2. This is 88. Where's 89? Oh. Okay? Yes. It has to do with so that this N says how far away it is from the nucleus. And Bohr would have said automatically that means higher in energy. So how do we follow the pattern to say, no, that's not true? Then we can do this. So these are closer to the nucleus than these, but they're higher in energy. Yes. So it's like a way to figure out the pattern. Yes. This is iron. Oh, yes. Oh, listen. Someone's trying to steal my thunder. So I'm going to pause the video. I want you guys right now to do lead. Some people choose to do it on the back of their paper. On that chart, you can do it on your own paper. Let's see. Okay, so we are going to do a short form way as well, okay? So, when you have atoms, then they lose or gain electrons, we often consider how they compare to a noble gas, right? And again, if you forget what the noble gases are, your periodic table tells you, okay? So we can use the noble gas to help write a shorthand electron configuration. So as you may have noticed, it's going to be the same every time. 1s2, 2s2, 2p6. That gets tedious, right? So if this is literally taken from my grade 11 note, okay? If sodium has 11 electrons, sodium's in the first column, it loses 1. It would have the same number of electrons as what element? 11 minus 1 is? Yes. Good. As neon. So we say that the sodium ion is isoelectronic with neon. Iso means the same number of electrons. In grade 11, we always compare to a noble gas. So we're going to do the same. We're going to use noble gases. However, the only annoying thing is, it's like the Price is Right. You can't go over, okay? So for example, something like chlorine, it's tempting to use argon, but it's over, right? It's got 18, so you have to go backwards. So you would still use neon and then have to write what's left over. So sometimes students are like, Ms. Todd, the short form isn't very short. Fair, okay? But we can't go over. So so you got to look backwards. Okay? That's what that means. So let's do the example. So let's do sodium. So sodium is 11. So same thing, 1s2, 2p, not right, 2s2, 2p6, 3s, how many? 1, okay? So again, you can be thinking all the time, okay, I know that sodium has one valence electron. Valence is the farthest, the highest N value, one electron. Isn't this the greatest thing ever? Yes. Let's do neon, which has 10. Neon ends at 2p6. So I'm going to try to line it up on purpose. Okay, so there is very little that's different. So for sodium, what can we do to make our lives easier? We can do the short form. So what you're going to do is use the noble gas. Okay, so the noble gas goes in the brackets. We're super lazy. You can write the word neon. Most people just put the noble gas's symbol. How many electrons does neon have? It has 10. So this would be like 10, and then we're going to write whatever's left. So this is the same. What's left over? Yes. Yes, whatever's left over, okay? Yes, because you still want, how many does sodium have total? 11. So you still have to have 11. So 10 plus 1. Okay, let's do chlorine, because chlorine's a little bit annoying. You're going to be like, that's less short than really, that's not very short, Miss Todd. Okay, so chlorine is number 17, okay? So that would mean 1s2, 2s2, etc., etc. 2p6, 3s2, and then 1, 2, 3, 4, 5. 17, okay? 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 7. You would know that chlorine has 7 valence electrons. In the third, there are 7. Okay, there's lots of ways to check your answer. Now, so this is the same as neon. Got a little excited there. But then there's a little bit more left over, okay? So you just have to keep going and write whatever's left. I can't use argon because argon is 18. That would break the rules. I want to win at the Price is Right electron configuration. So again, you can still count the total. 10 plus 2 plus 5 is 17. So you write the noble gas inside square brackets, and then what's left over, okay? So you'll be asked to do both. Write the longhand configuration, write the shorthand. So make sure you can do both. Yes. If it says shorthand's okay, yes. If it says longhand, you got to write it out, okay? But yeah. Yes, that would be it. So logically, is that probably what I'm going to give you? No. Yes. No, I was just trying to show you, like, this is the same, this is the same. Yeah. Yes. Yes. Always. Okay, so let's let's get this done, okay? So the one other way we are going to do this, and this does sort of say diagram, but basically it's the same pattern. So we're still going to do 1s2, 2s2. We're just going to show it using arrows, okay? So when I was in high school, I learned this using like these weird half arrows. I guess, we're so lazy I couldn't make a full arrow. If you are a textbook reader, your textbook uses this full arrow, okay? But it doesn't matter. You're trying to show and follow the spin rule. One spins up, the other spins down. Does it really matter which is which? No. There are 2 electrons maximum in an orbital, right? So one up, one down. That's all you need. So you are not going to do this or this. My pen does the up first and the down second, but that doesn't, see, I can't even do it, but it doesn't really matter. One's up, one's down, okay? What we'll do, I know there is spots for definitions, but actually I think it makes more sense to draw the diagram first, okay? So I'm going to skip to sulfur. We're going to do sulfur, okay? And then we'll write those out, I promise. So sulfur has 16 electrons. What do we always start with? What's first? 1s, 2. Then it would be 2s2, 2p6, that's 10. 3s2 is 12. How many go in sulfur's 3p? You really actually have 2 options. If this is 12, what's 16 minus 12? How many are left? 4, or you can go 1, 2, 3, 1, 2, 3, 4. Yes, I'm going to go back. I think it makes more sense. Okay, so when you do an energy level diagram, we're going to call this the off-bow principle, that you fill the lowest in energy first. So how do we show, like in a normal graph, low in energy? We go to the bottom, okay? So this means energy increasing, just like a normal graph, right? So how many go in the 1s? 2. You can draw, your pencil maybe does this, my pencil does not. See, nasty, I can't do it. I draw the up first. You can draw full arrows and not be a lazy chemist. It doesn't matter. Your textbook puts a circle around this. You can do that if you want to. You can use lines. It doesn't really matter. It doesn't really matter for the S. The big problem will be when we get to P and D, okay? Because there's only one S, right? So now we're going to do 2s. In an energy level diagram, you want to show more energy. How do we show it? Put it on top, okay? So these will take up a lot of geography on your piece of paper, because I need to know that you know 1s is lower in energy than 2s. How am I going to know? This is lower, and then this one is higher, okay? So whatever, do a line, do your circle if you want, whatever. Then we're going to 2p. So we have 6 total. So for electron configuration, all we had to do was write the 6. When you do the energy level diagrams, you don't have to say px, py, pz, but we do need to show there's 3. So this is where the lines or the circles might be helpful, okay? How many p's are there? 1, 2, 3, okay? Now, when the orbital is full, your life is easy. It's when we get to this one that things will get a little bit hairy. So there's something called Hund's rule, okay? So he said you fill up each orbital with 1 because they don't want to be together, and then you go back and pair them up. So even though this is 6 and it's full, that's how I'm going to do it. Okay? So 1 in each. I'm going to draw 3 ups. Who cares? Then I'm going to go back and pair them up. 2, 4, 6. Yes? Then we do 3s. To be honest, you can also do this. Like when I did it this way because this is the way your textbook did it. When I was young, we did it like this, where the S's were in a column, and then you did the P's sort of in another column to kind of separate them, but doesn't matter. Okay, so how many electrons go in the P? 3p, sorry. How many? 4. How did I know that? Where is sulfur? 1, 2, 3, 4. Okay? So now Hund's rule is vital. 1, 2, 3, 4. So it makes sense for 2 reasons you can think of it. If electrons have the same charge, they're going to repel. So why would they leave an empty orbital? They would not. Okay? The second thing, if I asked you, how many electrons does sulfur gain, what would you tell me? 2. If you look at this, is it obvious where they go? There's 2 spots. If you did this, it doesn't look as good, you know? Okay? So that's called Hund's rule. Yes, Abby? Yes, exactly. And for the same reason, repelling. Okay? Because if they're the same charge and there's an empty orbital, they're going to want to be apart. So they only pair up when they have to. Okay? In chemistry, if it's the same charge, it repels. So if you, let's say you did it this way. Oops. And this one was empty, then one of these would want to go over here, right? It would fill that up. So it could be apart, yes. It doesn't matter. You can do 1 up, 1 down. My pencil just does the ups first. Now, because these ones are full. So let's say you did neon, then this would be full as well. So just like with electron configuration, you just do as many as you have to get the total of 16. 2, 4, 6, 8, 10, 12, 14, 16. Yes? Well, what you can do is go back to this chart. Okay, so there's 1 S, 3 Ps, 5 Ds, and 7 Fs. What you can do now that you have more information is do like 2 divided by 2, which is 1. 6 divided by 2, which is 3. So if it was D and it's 10, how many lines would there be? 5. Okay? So you can do it that way too. Yeah. Whatever you're using to help you remember. Okay, so now let's write the definitions. We'll do this one first, okay? So instead of just saying electron is added to the lowest energy, we call that the Aufbau principle. Which is, this is, you're like, of course, Ms. Todd, obviously we've been doing this since for, yes, okay? So now we give it a fancy name, Aufbau. Technically, Aufbau is a German word. It's not a person, so you don't have to give it a capital. Lowest energy. Okay, so then the name for the rule where you have to half fill the orbitals first is called Hund's rule. And the person, and I think they talked about Pauli in the video, the person who said spin up, spin down, his name was Pauli, okay? So this sort of goes with the MS value of plus and minus a half, right? One goes up, one goes down, yes. Yeah, sorry. I had to squish, but I don't know why, because there's lots of space, so. Thank you. Yes. Yes. So that's like the constellation of that. Well, how do we stay in the same orbital? But if we're the same charge, we're going to spin up and spin down. Yep. And that's like the max. Then new orbitals. Yes. So that's what there is a chart, okay, that you can memorize if you want, or if you know, like, say that this is the S, then you always divide by 2. 2 columns, 2 divided by 2, 1. P has 6, 6 divided by 2, 3. Okay, 5 divided by, 10 divided by 2, 5. So then there will be 5 if it was D. Yes, yes. And it is that there is a chart at the start of the note. So you decide what you want to do, okay? Okay, so one of the things about energy level diagrams that to me looks a little bit better than electron configuration is how do we make an ion? You can do ions with electron configuration. You would just add or subtract the appropriate number of electrons. But I saved the ion examples for this section, okay? So that's what we're going to do next. We're going to do the sulfur ion. Sulfur's a non-metal, so it gains. So don't push out of your brain what you already know, right? You would know that sulfur gains 2. Yes. Yeah, so it would. It would get there and it would just repel as much as it could. Yeah. Because we think of electrons like circles, but they're really just packages of energy, you know? They're just doing their thing, moving fast, being small. Yes, energy. Is it a wave? Is it a particle? I don't know. That's why we still, even though there's so many observations we can do, it's still theoretical. So maybe one day that'll be your Nobel winning, and you can just say it all started with Mrs. Todd, and that's all I ask, you know, in your little speech. Okay, so let's do the ion. You have choice, okay? So I'm going to quickly sketch it again. If you would rather just add some color to your atom, it's up to you, okay? So sulfur gains 2 to have 18. And again, please, please, please don't push out of your brain what you already know. You would look at sulfur and you would know that it's -2. You would know, okay? We did so much crisscrossing last year, right? Hated it. That's why we need it, okay? So let's do it. So we have 1s, 2s, 2p, 3s, 3p, look at my lazy arrows. Terrible. Who cares? It looks beautiful, okay? It does take up, like I said, quite a bit of geography on your page, but the better you spread it out, then it's a bit easier to tell, okay? I have lots of line paper if you need some. You know, maybe your guardians are like, that's enough paper. You tell that Miss Todd. I'll give you some, okay? I think that gaining electrons is easy to show. Where does it go? Oh, they obviously go here. And just remember, if I've drawn these both up, so the ones that come in will spin down. So if you did it opposite and you spun yours down first, then make sure the ones you add go up, okay? Still have to follow Pauli's rule. Yes? Whatever, yeah, so I did, yes? And it just has to be opposite to what you have drawn. If you didn't draw them up, if you drew them down, then you would draw, you know what I mean? Do the opposite. You don't have to make them a different color. I just like coloricity in my notes, okay? So okay, so sometimes, I know it says there gaining electrons is easy to show on an energy level diagram. It's not that losing electrons isn't easy to show, but again, we don't want to say skip the transition metals anymore. So how can we deal with the transition metals? And once we draw the diagram, you'll be like, oh, that makes so much sense, okay? So serendipitously, I chose zinc to do our example, and now zinc's on here too. Beautiful. So wherever you wrote zinc, if it's on your electron table or whatever, take a look. Let's draw the diagram. Oh, I already have this here too. Perfect. How many go in zinc's 3D? 10, so it looks full, yeah? I forgot to write that there's 30 electrons there for zinc. Yes. Yep, sorry. 2, 4, I should have checked. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, so this looks full. Zinc, zinc is a transition metal, so it's tricky. We cannot count the columns. If you use our periodic table, how do you find the charge? It's underneath the symbol, so zinc says 2, okay? So normally if you're asked to do an ion, it'll give it to you like this. Like it'll write the charge for you in the homework, okay? So you don't have to guess. It'll tell you what the charge is going to be, I think usually in your textbook. So how do we know which electrons to lose? Okay, so get out your highlighter. So electrons are going to lose, sorry, elements are going to lose electrons that are farthest from the nucleus. How do we know which ones are farthest from the nucleus? Yes. Close. The one on top is going to be the highest in energy. How do we know it's farthest from the nucleus? Largest N value. Okay, so zinc has to lose 2 electrons? Yes. But the distance from the nucleus. So in Bohr, it would be like the orbit, but now we make shapes inside that orbit. So it's the same as what he would have done before, like N is 1, 2, 3, 4. And it corresponds, like, you know, when you did the Bohr-Rutherford diagrams, you would have said row 1 has 1, row 2 has 2 shells because of the N value. So it's the distance from the nucleus. Okay, so let's go back just for a second. Of these here, which one has the highest N value? Four S. How many are in 4S on zinc? 2. How many is zinc supposed to lose? 2. There is cases where the farthest from the nucleus, the highest N value, will be the top. But then, of course, the ones that were weird, like transition metals before, where we would have said, skip those. Now, let's not skip them, okay? So when you go to draw the ion diagram, it's up to you. Some people will leave a blank line to kind of be like, you know, energy level accounting, you know what I mean? Some people just won't write it at all. It's kind of up to you, okay? So I'll just let people get that, and then or you can try it. Yeah. I think there's a spot, right, in this one? Yes. Yes. Then you would do the one that was at the top. Yeah, and there's lots of them that are like that, that it doesn't matter. It's just obvious. Yeah. based on the charge. So because it says 2 plus, then just lose the 2. If it was 3, then you would do these ones and then one of these or something weird. Okay? Okay, so I'm going to draw the ion. Please, please, please. I know I said we would get to do work, but try some of this homework this weekend.